Well, welcome to the Analytical Chemistry Lab. That's where I am right now, and I'm going to talk a little bit about some applications of acid-base reactions and give us a little bit more background into weak acids, weak bases, and thinking about aqueous solutions and how reactions occur in aqueous solutions, which then we're going to connect to how we quantify different species within a solution, maybe thinking about pH or different measurements that we may be making. So now what we want to do is we want to start with, I just wanted to remind us about all the different relationships that we have. So again, we have all these relationships that give us the ability to connect pH, pOH, hydroxide activity, hydronium activity, and then how all four of those variables relate to each other, in addition to the relationship between maybe the hydroxide concentration and the activity of that using the activity coefficient. So my goal in this video is to go through some practice problems and some examples and think through some of these topics and questions we ask ourselves as we're analyzing a solution. So let's first start by looking at our first one here, and we're going to look at formic acid. And formic acid is a monoprotic acid naturally found in bee and ant stings. And a student was investigating some of the chemical properties of formic acid and prepared a 0.150 molarity aqueous solution of formic acid. To give this solution a similar ionic strength to blood, the student added sodium chloride to give a sodium chloride concentration of 0.154 molarity. Now what that's going to do is that's going to influence our ionic strength. The student labeled this solution F. Now we want to identify the pH of this solution. So we first want to think about what are these different solutes that we have. So we have formic acid. And I'm going to write, just to save myself some time, just formic acid is HA. So we have our formic acid here, and we see that formic acid is going to undergo a reaction with water to give us the hydronium ion, and then the formate ion, our anion here. So now we have our reaction, and we see that this reaction is going to produce some amount of the formate ion. It's going to produce some amount of hydronium. Now that's dictated by what our Ka value would be, or if it's a strong acid. So we could go to, we first look at that and we think, okay, is this going to be a one-way reaction like we'd see with maybe nitric acid? Does it undergo some equilibrium? So I go to a Ka table and I find that I have a Ka of 1.80 times 10 to the negative fourth. What that lets me know is that this is a weak acid. So now we have a weak acid in solution. That's what our formic acid is going to do. Then we also have sodium chloride. Sodium chloride is something that is very soluble in water. We're told that we have a specific concentration of it. That means that it did dissolve. And as it does that, it's going to dissociate into our sodium and our chloride ions. Now what that's going to do is that's going to influence what our ionic strength is for our solution. So we start with those two things, and we see that we have our sodium chloride dissociating into sodium and chloride ions, not necessarily producing hydroxide or hydronium, so we wouldn't necessarily focus on those as part of our pH relationships. And then we have our formate ion undergoing this reaction, our formic acid undergoing this reaction to produce hydronium and the formate ion. And it is a weak acid equilibrium reaction. So we think, how are these two variables going to relate with each other? And if I want to quantify pH, if I think, what does that mean for me? That means I need to know the activity of the hydrogen ion, or H3O+, right? Remember, we can use those interchangeably. Once we know that, or the activity of our hydroxide ion, we also can quantify pH from there. But we see that we're making the hydronium ion, and we're undergoing this equilibrium reaction. So we want to start by setting up our equilibrium table that we have here. So again, we ignore water. We have 0.150 molarity. We didn't directly add in any one of those two species. And so then we're going to have some amount reacting to produce the formate ion, and we're going to get rid of some amount of the formic acid. Now, reminding us, these are the actual concentrations at equilibrium. So that would be like the concentration of our formate ion, that would be the concentration of our H3O+. This would be the concentration of our formic ion, a formic acid, all at equilibrium. And so then we think, okay, how is my sodium chloride going to influence this? What's this going to do is it's going to influence the ionic strength of my solution. If we went through that ionic strength calculation, we'd find, based upon the concentration that we have here, our ionic strength is 0.154 molarity. Now we also have some amounts of these ions present, but we don't know yet. We don't have an idea of what those concentrations are, so we couldn't necessarily include those as part of our ionic strength. Right? All we know is that we have these sodium chloride ions producing a lot of ions, greatly influencing our ionic strength. Now, what does that do to the solution? What does that do to what's part of our equilibrium, the hydronium, the formate ion, and a formic acid? What that's going to do is that's going to influence what the activity coefficient is, right? Because increasing our ionic strength is going to reduce the activity or reduce the activity coefficient. That's how we express that mathematically for our ions here, the hydronium and the A-, the formate ions. We went through that calculation. We would find that the activity coefficient of our H3O+ is 0.808. And the activity coefficient of our formate ion is 0.747. And again, we can use the effective diameters and the Debye-Huckel equation to calculate that. I'm just not going to explicitly show that here. So now we have these activity coefficients, and let's go here and think about, well, what is the activity coefficient of our neutral species? Now, our neutral species, we think about what activity is. Activity is a measurement of how much our charge is reduced, or the effective concentration of that charged species is reduced when we have all these other ions present in solution. And so for the most part, unless we're dealing with extremely high ionic strength solutions, we would see that our actual concentration and our activity, the relative reactivity of that specific neutral species, in this case the formic acid, will be 1. We can make that approximation here for our neutral species. And we see that we can do that because there's no necessarily ionic cloud per se present around that's going to be influenced by the sodium or chloride ions to the extent that we would see for our hydronium or the formate ions. So now we have our activities, and now all we have to do is plug in the information that we have presented so far. So we have our Ka is equal to the activity of our hydronium ion, the activity of our formate ion divided by the activity of our formic acid. And so we can go ahead and plug in the information that we have here, 1.80 times 10 to the negative 4th equals the activity of our H3O+, so that's going to be our 0.808. So that's our activity coefficient times the concentration we'd have X, the activity coefficient of the formate ion and the concentration we set at equilibrium of X, and then the activity coefficient of our formic acid, and then the concentration that we would have at equilibrium. So now we have an expression. We got to do some algebra. I'm just going to zoom through this in our video, showing this step by step if you'd like to watch it, and then see what our solution would be. So now we found that the X value is 0.00654, and we think, well, maybe I could have just done the approximation and ignored that minus X and simplified our math, but what we would have seen is that that actually would have changed the relative amount of that specific concentration. So that would have gave us 0.144, which is not, that's almost a significant relative to what we started with regards to our original solution. So we couldn't just ignore that minus X. We'll see that maybe there are certain circumstances that we could do that just to simplify the math application, that we would get the same answer. Well, now that we have our X value, or the concentration of our H3O+ and the concentration of A-, what we can then do is then we can go ahead and find our pH, right, as the negative log of our activity. So negative log of our activity coefficient, 0.808, and the concentration of our H3O+. And so we'd find that we get a pH of 2.277. Now, as we look at this, what we would see is that, well, now that we actually measured, we said we have some relative amount of H3O plus and A minus, what we'll see is that if we included that, let's say we redid this whole process and thought about how will those influence our ionic strength? Will they influence our ionic strength? And if we look at that now, we kind of take that information, what we'll find is that our ionic strength, once we include the A minus, our formic ion, and the hydronium ion, so now once we include that, our ionic strength is now going to be 0.160 molarity because of the inclusion of our H3O plus and our A minus, the formic ion. Now what does that do to our gamma values? That's going to give us a gamma of H3O plus of 0.807, a gamma value of our A minus of 0.744. And we see that kind of changes our activity coefficients, not very much. If we went ahead and just kind of redid and used those to calculate our new pH, we did this whole process again with our new activity coefficients, we're going to get a pH of 2.289. So slightly different, and we could redo that again with our new concentrations, but we'll see is that if we see that we significantly change our activity coefficients, we significantly change our ionic strength because now we're including the amount produced from that weak acid in this case, then we can include that and we see it's going to influence the pH of our solution that we would see represented by the actual ionic strength of our solution. And then we could go ahead and do that again and we'd see that our pH is not going to change. So sometimes we could see that we could do this iteration. At this point in time, we're just looking at our first iteration. We may have to redo that multiple times if we are thinking of the possibility of producing a significant amount of ions when we look at our weak acid or a weak base ionization reactions. So now that we have that kind of in mind and the thought process that we have, let's think about, well, what happens if this student now wants to do some kind of test on this formic acid solution. So they're going to look at the efficacy of some basic antiseptic, and we want to think, what is that going to do to the chemistry of the solution that we have, the chemistry of the bee sting that we would be looking at here. And to do this, the student replicates this by adding 10 milliliters of 12 molar potassium hydroxide to 1 liters of solution F, reminding us our solution F is 0.150 molarity of our formic acid and 0.154 molarity of our sodium chloride. So we have that solution. To that we're adding to all of this, and again we have 1 liter of that. We're going to add 10 milliliters of our 12 molar potassium hydroxide. So now we look here and we see that we now have added this potassium hydroxide. Our next question is, well, what is that going to do to our solution? And we see that we're adding, again, look at our solutes, and we see we're adding a strong base. When we add that strong base, what is that going to do? Well, we have an acid present in our solution. So when we add a strong base, it's going to find wherever our acid is present and it's going to gobble those up and react with them. And so now let's look at, well, what kind of reaction will we have? We have our acid reacting with our strong base, and we add this strong base, it's going to completely react with whatever amount of acid that we have, as long as our strong base is our limiting reactant. So we're going to react away our acid with the amount of base that we have added. If we've added an excess of base, we will react all of the acids. We need to look at the relative amounts or the limiting reactant here. So now we have our reaction, and in our reaction, we're going to now produce potassium ions, our formate ions, and water. And I'm just writing these explicitly out to show us that we're producing more ions, so this is maybe going to influence what our ionic strength of our solution is. So now we have our solution here, and what we notice is that we're reacting some amount away. So let's figure out how much we're reacting away. So as we look at this, we see, because I have 1 liter of my solution, that would mean if we look at our moles equals our molarity times our volume in liters, that we actually also, if we can simplify this and say we have 0.154 moles of sodium chloride, 0.150 moles of our formic acid. And then if we go ahead and do a quick calculation here, we find that we're adding 0.12 moles of potassium hydroxide. So we're adding that much. So let's do a quick kind of before our reaction and after our reaction, kind of like a thought process. Actually, let's look at before our change and our after, kind of like an ice table. We're not really ending up at equilibrium. We're looking at kind of a full reaction here. So before our reaction happens, we started with 0.150 moles of our acid, 0.120 moles of our base. We didn't necessarily have these per se when we're looking at our reaction and we're dealing with water. We don't really necessarily focus on that. Now again, this is an oversimplification in saying that we don't have any of that formate ion, because in actuality we did have a very small amount, which we already calculated. But we're looking at, we're going to see the vast majority of our formate ion that we're going to have in solution now is going to be produced from this acid-base neutralization reaction. So then we look at, okay, how will they change? We're going to see that the most that each of these can change is by 0.12, because we have potassium hydroxide is our limiting reactant. And we look at our stoichiometry here, that's going to produce 0.12 of our potassium and our A-, as well as some water, but we already have tons and tons and tons of moles of water already, like 55 moles of water in our 1 liter of solution. And so then now we look at that here, and we see that now we're going to have 0.030, no potassium hydroxide left over, 0.12 and 0.12 moles of our potassium and our A- ions. So now that we have that information, we are going to now look at, well, how is that going to influence what our equilibrium is? So now again, we go back and we think, what reactions are present? What is our ionic strength? How does that correspond to the things present in solution? And if we just think conceptually real quick, if we just draw a beaker out of what our solution looks like, we have still some weak acid. We have a bunch more of the conjugate base now, that formate ion. We have potassium ions. We have chloride ions and sodium ions from our original solution that we added. And so we see we have all these. Obviously this is dissolved in water. We're not necessarily including any of our hydroxide ions, because we see that those have all reacted. And so we think, okay, now what is going to be part of our acid-base equilibrium, and what's going to contribute possibly to our ionic strength? So we would see our HA and A- are they going to be involved in our acid-base equilibrium. And then we think, okay, what's going to contribute to the ionic strength of our solution? And all of the ions are going to contribute to the ionic strength of our solution. So we can't just exclude our A-. We see we actually have a bunch of it now. We have about 1.12 molarity in our solution. And so now that we have those kind of thought processes, we're going to do a very similar thought process that we just did when we thought about just our weak acid solution with the sodium chloride in it. We're going to look at our equilibrium reaction. So we have our HA. And I'm going to just kind of give us different views of how we can write this. I'm going to simplify it by not writing out water. Again, reminding us this is the same as the reaction that I just wrote before. We're just showing that it's not really dissociating, it's really reacting with water, and this is the same thing as H3O+. Okay, I just want to give us different viewpoints of here, how we can see that. So let's go ahead and fill in our ice table and then solve for X. And I'm just going to go ahead and zoom through that real quick. So also looking at this, reminding us that we need to think of our ionic strength. So if we recalculate our ionic strength, we would find that it's 0.274 now, with the addition of the potassium hydroxide and the formation of more formate ion. And what that does is that's going to influence what our gamma values are. So the gamma value of our H3O plus now is 0.786, and the gamma value of our formate ion is 0.708, which we now have included as part of our equilibrium expression here. Now we look at this and we want to think, okay, I have a pretty good amount of A minus. I have a smaller amount of HA, but we think, okay, this is an equilibrium reaction. Our Ka is relatively small. And what that means is that I have a smaller amount of products at equilibrium than reactants. And if I already have a lot of product relative to my reactants, that means that this increase here is going to be very, very small. And that's because we already have a bunch of the A minus present in there. Now, what does that mean for us? In our previous example, we did not exclude the minus X, but here what we're gonna do is we can actually ignore that plus and minus X to say this is about 0.12 and this is still 0.03, because that minus X or plus X is not going to significantly change that number. And we thought through this and just saving us some time in math, and that because our Ka is very small, the amount of product that we're going to add to what we already have of our product, the formate ion, is going to be relatively small. So what does that mean for us? That simplifies our math a little bit here. There's no quadratic needed, there's no x squared, there's just an easier solution here. And we go ahead and do a really quick plug it into our calculator, and we get 8.09 times 10 to the negative fifth for our concentration. Then we go back and we see, okay, was that an okay approximation? Well, if we were to think of that as 0.12 plus 0.1234809, that's our 8.09 times 10 to the negative fifth, we see that because our precision only goes to the third decimal place, effectively it doesn't change it. And we can make that same conclusion with our 0.03, so that's why it made sense for us to ignore that. So we always go back and check to make sure, was our approximation okay? And in this case it was. Well, now that we have our concentration there, we'll go ahead and calculate our pH again, the negative log of our activity, so 0.786 times our 8.09 times 10 to the negative fifth, and we get a pH of 4.197. Now, as you look at this, we see, okay, our pH went up. That made sense because we added a base. But we look at it and we think we added a lot of base, and it's not significantly changing it to become basic or almost not acidic. And maybe we look at this and maybe as I was writing through this, you looked at that and you said, hey, wait a minute. I have a lot of weak acid and conjugate base. That's a buffer. A buffer contains a lot of acid and a lot of conjugate base, relative similar amounts of them. And so you think, well, can I just use the Henderson-Hasselbalch equation? Can I just think I have a buffer, I have a significant amount of acid and conjugate base? And we say, yes, we can. We actually can do that, where we could use the pH equals our pKa plus the log of our activity of A minus, activity of HA, right? So now, and again, usually when we saw the Henderson-Hasselbalch, we're just looking at concentrations, but we're thinking about how our activity is part of this as well. And because this is a neutral species, we would also see that that's the actual concentration of our weak acid, but because we have our A minus, the formate ion, that activity is influenced there. So we could go ahead and do the simplification. In theory, if the Henderson-Hasselbalch equation applies here, we should get the same result. So our pKa is 3.745 plus the log of our activity of the A minus, so that would be 0.708 times our 0.12, and then we had 0.03 for our concentration of the HA, and we go ahead and plug that into our calculators and we get 4.197 as well. And so we see here, we could have saved our time, ourselves a little bit of time and heartache there to look at the kind of extra math that would go with that. But anytime we see that we have a lot of an acid and its conjugate base, and a weak acid conjugate base, or a weak base and its conjugate acid, we have the ability to apply the Henderson-Hasselbalch equation here, and either one give us that same analysis. But before we do that, we got to figure out what's present in the solution. Okay, so this gives us a chance to maybe see and work through some of these problems together and thinking through them. So I'm going to have you this practice on your own, and I will be posting the solutions at a later point for us to think through this, because I want you to kind of focus through it. So I'm going to read it through, give us some hints, and then let us go with it. So many of the natural geysers in Yellowstone National Park, this comes from, I was just in Yellowstone in this last summer, have boiling hot water that is also very acidic. A student researcher wanted to investigate the relative concentrations of the acid-containing species. So in this case, the pool was primarily found to contain sulfuric acid as the source of acid that we see here. And they did some analysis and they found the total sulfate concentration. So think about our mass balance of sulfate. Anything containing sulfate, our sulfuric acid, the bisulfate, and the sulfate ion is 0.0445. And what that means is that those concentrations are equal to 0.0445, the sum of them. And the ionic strength of the solution was 0.093 with a pH of 0.15. So from that information, we want to find out, well, what is the actual amounts of each of these in the pool water? And we know some information about sulfuric acid. Ka1 is very large, meaning that it is a strong acid, so effectively it completely ionizes for that first proton. And Ka2 is 1.99. So once you go ahead and take that information and work through this problem and think about, can we identify the actual amounts of each of those different species, the sulfuric acid, HSO4 and SO4 minus, at equilibrium in our solution here with a pH of 1.5. So best of luck with that, and I will be posting our solutions in a little bit.